Hi everyone, my name is Raksha and this is my Physics 2 lab report for Lab 2 on line charges. So this lab is pretty much building off of our previous Lab 1, and so we'll look at the summary of my Lab 1 results and talk about what's different in Lab 2. So for this lab, our aim is still to determine the amount of excess charge, which is the amount of excess or deficient electrons. However, the difference is that this time we'll be modeling each piece of tape as a line charge instead of a point charge, which we did previously in Lab 1. And in terms of different physics fundamental principles that we're using, we'll still be using Coulomb's law, which requires an understanding of electric fields, forces, and point charges, gravitational law, and Newton's second law, in which we assume that the sum of the forces is zero, and this later on helps us calculate a gravitational electric force, and then Newton's third law, in which we know that the top and bottom tapes have equal and opposite forces to each other. So a summary of some important results that I got from Lab 1. I got that the length of the tape was 20 centimeters, and then given that this length, we can calculate the mass to be 0.2 grams, and then the distance between the tapes was 0.16 meters, and the magnitude of gravitational force is equal to the magnitude of electric force, and we get a result of 0.001962 newtons. And here are the formulas for the fundamental physics principles that I talked about that we'll be applying in this lab. So a quick recap of the calculations I did in Lab 1. I'll go over this a little bit more quickly since I talked about it more in detail in Lab 1. So I mentioned before our length of our tape, and then we were given the density, so based off of our density and the length of the tape, we can calculate the mass. And the distance between the two tapes when one of the tapes began to flow above the other is here, and then the magnitude of gravitational force is equal to mass times acceleration due to gravity, and then the magnitude of the electric force is equal to gravitational force, and then we can equate these two equations together to solve for the charge on tape B, and we get this value, and this is equating both equations together. Some assumptions for this lab are that we'll be ignoring air resistance, and we'll assume that the tape had pretty much the same amount of charge evenly distributed along its entire length. Moving on to the coding for this lab. So here is the link to the full code, my full Go script, so you can look at it more in detail if you want to. Here's a couple of screenshots showing the important parts of the code. So first we calculate the physical constants that we need for the entire lab. Then we have a function to calculate the electric field, another function to calculate the line charge, and then we use this function to calculate the line charge for both the top and the bottom tape. After we do that, we can calculate the net electric force. We consider both the x and y axes this time, and then we also calculate the forces that the tapes have on each other, and then we include gravitational force as well, and then after that we get an output, and this is the Lab 2 output that I got. And this is the output from Lab 1, so we can see the difference from the output, and because Lab 1 we assumed it was a point charge, whereas in Lab 2 you can see that we assumed that it was a line charge, and that's why we also get, as you'll see soon, a different charge on the tape. So answering some final questions as our conclusion. We did get different results for Lab 1 and 2. In Lab 1 we assumed it was a point charge, and we got this result. I forgot to add coulombs here, but it's coulombs. And then in our second lab we assumed it was a line charge, and so we got this result. And the reasons that they differ is, like we explained, in one lab we assumed it was a point charge, and in another lab we assumed it was a line charge. And in terms of which value is more likely to be closer to the real value, I'd say the line charge model is more accurate because it takes into account all the small charges in the electric field on both the axes, and so it's more accurate than the point charge module.